In this video, we're going to take a look at the drag force, or sometimes it's known as the resistive force. And so the equation is Fr for resistive equals negative kV. However, sometimes the equation is written Fd for drag is equal to negative some other letter, B is a very common one, times V as well. Let's jump right into a problem. A sled of mass m is being pulled to the right across ice by an applied force Fa. The sled experiences a resistive force from the air of magnitude kV, where k is a positive constant, but no friction from the ice. Express answers in terms of given quantities and fundamental constants. Okay, so a sled being pulled by an applied force. Pretty simple. And already I know that that force means I'm probably going to have to draw a free body diagram. Let's take a look at what A asks us to do. Write but do not solve a differential equation that can be used to find V as a function of time. Okay, so ultimately I want to get V equals something, but this thing right here, write but do not solve, this is a very specific prompt. It wants me to look at the forces acting on the object, and so I'll draw a free body diagram. Fa is the applied force to the right. Then there will be a drag force, which I'm just going to label kV since that's what they gave us here. And then a weight force will be down because gravity is pulling the object down. There's going to be a normal force up. And I know that since it's on flat ground, the normal force and the weight force are equal, so they're not going to give anything to the net force. And the net force is actually how we're going to get to an equation that we can use to solve for the velocity. If you forget what that is, the net force equation is sigma F, or net force, equals mass times acceleration. Now, the net force, it's pretty easy to see what it is. It's the applied force minus that drag. And so we'll write that on the left-hand side, Fa minus kV. And the mass is going to stay the same, but what do I do about this differential equation thing? Well, this is a call for you to do something very specific. It wants you to express the acceleration A as a derivative of something that's already in the equation. And so if I look here, I have V, and I know that acceleration is the first derivative of V with respect to time. And now what I have is an equation that has velocity and its derivative in it. This is called a differential equation, and since it has the function V and its first derivative, we call this a first order differential equation, or diffy-EQ is also what they're often called. Great job, we did it, let's move on. Okay, what about the terminal velocity? Well, terminal velocity is like the maximum speed that you're going to get. And since the resistive or the drag force depends on velocity, then as the sled begins to speed up, so will that resistance. It'll get bigger and bigger. So eventually, I'm going to draw the sled. This looks like a terrible sled. It's like an elephant shoe. Eventually, you have your applied force forward. The drag force is going to get so big that it's actually equal to the applied force. So you'll have what we call a terminal velocity Vt when those two forces are equal or the acceleration is 0. So what will the expression look like? Well, basically, I've got Fa minus Kv equals 0 instead of Ma, which is like saying that Fa is equal, terminal velocity. Fa is equal to our constant K times Vt. And solving for the terminal velocity, we get the applied force over the constant K. This is our equation for terminal velocity. That's a really easy thing to use, and we're going to use it in the harder part of the problem, which we're going to do now. Take a deep breath. Use your differential equation to solve for the velocity V as a function of time. Okay, so this is the hard part of the drag force problem, and I'm going to do my best to write down any equations that I'm using so that you don't get too lost, but try to stick with me. Okay, we have our differential equation that we wrote from part A, which is Fa minus Kv equals m dv over dt. We've got that. What we want to do is basically get V by itself and then separate the dv and the dt. This is what's known as separation of variables. Very Googleable, and you have to say Google like Google. Separation of variables. So let's do that. Let's get V by itself and then separate the dv and the dt. To get V by itself, I'm going to do two things. First, I'm going to factor out the negative, and then I'm going to factor out the k. So if I pull negative k out, then I'm going to have to divide this applied force by negative k. And then this will become a plus V. And I'll have m dv over dt. So we got V by itself. Great. It's in here, right here, just chilling. It's positive, no constant in front of it. How do we separate dv and dt? Well, to do that, we're going to have to get this m over on the left side. So I'm going to have negative k over m. And I'm going to clean up what's inside of my parentheses because I don't like what it looks like. I'm going to write this as v minus fa over k. That looks a little bit better to me. Oh, but wait. We said that terminal velocity is the applied force Fa over k. So to make things simpler and to write fewer letters, why don't we just call this Vt, terminal velocity for now. Okay, great. You definitely have a choice in what's happening in this video. Just kidding. Okay, so all that's equal to dv dt, and now we can separate the dv and the dt. Basically, all I'm going to do is I'm going to swap what's in parentheses with the dt, and I'm going to give myself a little bit more room to do that right now. Okay, so when I do this, I'm going to get negative k over m dt equals dv over v minus vt. Okay, fantastic. All right, now we have kind of like a weird thing, but we have a dt and a dv on both sides. So when you're doing the separation of variables thing, the idea is that you are going to integrate both sides. So I'm going to put a summa on the left and a summa on the right. Now I have to integrate from something to something, and so I'm going to start my integration from 0 for each, and then what I'm going to do is I'm going to go to t on the left because I want an equation for t on the left, and v on the right because I want an equation for v on the right. Pretty simple and straightforward. All right, well, how do I take care of this awful integral right here? It looks so gross. Well, this is when we're going to use an equation that would be given to us, usually in something called a table of information. So this is called a table integral. If we have the table integral written, it's usually written for x. So example, the derivative, or the antiderivative with respect to x of x plus a, or 1 over x plus a. This is usually given, it's given on the AP equation sheet, for example. This will be equal to the natural log of x plus a. So you don't have to memorize this equation, you just have to be able to use it. And basically, we've written our equation so that it's already in this good form. Instead of x, we have v, and instead of a, we have negative vt. So when I integrate the left side, what I'm going to get, and I'll scoot this up, what I'm going to get is natural log of v minus vt. That's it. Now I do have to evaluate that from 0 to v, which we'll do in a second, and it's a little gross. Now let's handle the left side. When I take a look at this, basically k and m are constants, so they come out. I can move this if I want to, like that, 0 to t. And the integral, or the antiderivative of dt, is just t. So what I'm going to get is negative k over m t, and I evaluate that from 0 to t. Okay, so let's do that. This is going to kind of take a lot of simplifying, but basically I'll have negative k t over m minus k times 0 over m. Well, that's just 0, so I'm going to get rid of it, erase it. So that's my left-hand side. My right-hand side is going to be equal to the natural log of v, I plug in v, minus vt, minus the natural log of 0 minus vt. Now here we run into a problem. 0 minus vt isn't 0. In fact, it's just going to be negative vt. So I can't get rid of that logarithm. So to simplify, we need to use a logarithm rule where log a minus log b is equal to log a over b divided by b. So I'll rewrite the right side as the natural log of v minus vt over negative vt, and I'll keep the left side the same. There's some simplifying I can do to this natural log, I already see. I'm going to want to write this as the natural log of v, well, I'll make that negative v over vt, plus 1, which I think I might just go ahead and write that as 1 minus v over vt. Oh, what was that? 1 minus v over vt. And again, the left side stays the same. So negative kt over m. Where do I go from here? Well, we want to get v, and it's inside of this natural logarithm. So what we have to do is raise both sides to the power of e. When I raise both sides to the power of e, what's going to happen is that I'm going to get e to the negative kt over m is equal to 1 minus v over vt. Pretty simple and straightforward. Okay, we still have to solve for v. How do we do that? Well, I've got minus v over vt, so I'm going to add that to the left side. V over vt equals 1, and then I'm going to subtract the e to the right side. E negative kt over m. Okay, we're getting closer. All I have to do is multiply both sides by vt. So I'm going to bring this up here to do that. V equals vt times, no idea what happened there. Anyway, times 1 minus e to the negative kt over m. And boom, we have our our velocity equation with terminal velocity inside of it. A lot of the times that you're asked about this problem, though, they don't want you to have vt in it, and so you'll replace vt with what we wrote down before, the applied force over k, 1 minus e to the negative kt over m. But you want to remember that Fa over k, that is the terminal velocity. And if you didn't know this, when you have e to the 0, it just equals 1. So in that case, when we start with t is equal to 0, then this whole term becomes 0, this whole thing becomes 1, and we get 1 minus 1 is 0, and so our velocity is 0, which just tells us that our initial velocity is 0. However, what's interesting about e is when you have e to some really, really big number, we'll just say it like that, then it's basically just going to give you 0. And so, as you approach 0, this whole term will go away, and what you'll have is Fa over k, or the terminal velocity, times 1. And so the velocity approaches the terminal velocity. So let's circle this equation real quick, make sure we've got it, and then let's kind of sketch what I just talked about with the velocity versus time graph. Basically, when time is 0, you're going to have 0 velocity. But eventually, you're going to start slowing down until you reach a terminal velocity here that we call vt. Or I can call that the applied force over k. So the reason why this is called terminal velocity, it's kind of easy to see with this graph, is you basically approach a limiting speed. You have an asymptote, a horizontal asymptote, and you can't get any faster than that. Okay, so we've derived this equation, and we've come up with this graph. The last thing for us to do is to think about what the position and acceleration equations would look like as functions of time. So I know that the position, let's do the velocity first, the acceleration first. That's a lot easier. Acceleration is the derivative of the velocity function with respect to time. And so if I take the derivative with respect to time of that function, we'll leave the vt in it. It's a little bit easier, I think, this way. E to the negative k kt over m. When I take that derivative, basically what I'm going to do is I'm going to use a really simple derivative rule. If you don't know it, it's given to you on the AP equation sheet. And we'll write it like this. D dx e to the ax equals a e to the ax, which is a combination of the chain rule and the derivative of e. But basically the derivative of e is itself. And so what I'm going to get for this equation is pretty straightforward. It's going to be vt goes away. So this will combine to vt and it'll go away. And then I'm going to have the derivative of vt times negative e kt over m. So just for the sake of expediency, I'll kind of do this a little bit faster than I normally would. But you're going to bring down the a, which is negative k over m, and then you have this negative right here, which will become positive. So you're going to have a positive k over m. You'll have that vt also. And then e to the negative kt over m stays the same. But remember that the terminal velocity, which I've written terrible here, is Fa over k. So I'm going to have Fa over k times k over m. Those k's cancel. And what I'm left with is that the acceleration equation is equal to the applied force divided by mass, which makes sense because force divided by mass will give me an acceleration, times e to the negative kt over m. Okay, great. Now let's talk about the position equation. This one's a little weirder, but the position is going to be the antiderivative of the velocity equation with respect to time. And for this, you would usually have a table integral that gives you the reverse, and it would say the antiderivative of e to the ax with respect to x is equal to 1 over a e to the ax. And when I apply that to my antiderivative, it's kind of strange. Basically, what I'm going to get is the antiderivative of, you know what, we got to pull the vt out. So there's vt. 1 minus e to the negative kt over m dt. And I'll need to do bounds, so I'll go from some 0 to some time t. When I take the antiderivative of this, I'm basically going to get my constant terminal velocity times a t, so that 1 becomes t. And then when I apply this rule right here to my exponent, or whatever, my e, I'm going to end up getting a positive, not k over m, but m over k. So I flip that. E to the negative kt over m. And I have to evaluate this from 0 to t, which again gives me something goofy, because when I plug in t into these two things, it just stays t, but when I plug in 0, I'm going to get e to the 0, which is 1, and so that's going to give me an mk. So again, for the sake of expediency, I'm just going to put this out, pause, maybe try and explain this to yourself if you want, or prove it, but you're going to end up with t plus m over k, e to the negative kt over m, minus vt m over k, which I'll stop there. We could replace vt if we wanted to, but this is good enough for us to kind of talk about what the graphs are going to look like. So I have an acceleration equation that looks like this, and a position equation that looks like this. So basically, if I was going to graph these, for my position equation, I would put something in that's going to have a t, an e to the negative t, and this would just be a constant, so we can say it's a 1. So if I put a similar graph like this into my calculator with x, e to the negative x, minus 1, I can get a general idea of the shape. And the general idea of the shape is going to look like this, where we have an exponential curve in the beginning, and then by the end, it sort of straightens out, which makes sense because the slope should be constant. Once you reach terminal velocity, you have a constant velocity. So let's sketch that for our position versus time graph. That's what it wants us to do for D. So it's going to go like this. And you could argue that there's an asymptote, maybe like a diagonal asymptote here, but this is just going to be constant slope at some point. You could acknowledge that if you wanted to. It's not super necessary. We already talked about the velocity function. Looks like this, where you reach the terminal velocity, which is Fa over k. But what about this acceleration equation right here? Well, this acceleration equation is a special kind of equation. Whenever you have e to a negative exponent, you're going to get a graph that looks like this. This is what's known as an exponential decay function. And notice that it doesn't start with a vertical asymptote. It actually starts at a specific value. And so on this graph, I'm going to point out that value is this F over m. Fa, applied force A, over m, which would basically be like what you would use to find the acceleration if there was no friction at all. Because at that very first instant, there's almost no friction at all. And so you would just take the applied force and divide it by the mass. But then after that, the acceleration, it actually decreases with that decay function until it gets to 0. Now, again, the object isn't at rest at that point. It's moving. It's just not going to get any faster because the forces have canceled out at that point. Okay. This is probably one of the most difficult problems you can do in introductory mechanics, and so congratulations to you, the person who actually made it to this point in the video. Everybody else is sad that they didn't learn all this awesome physics, and you are super great and are going to get the job of your dreams and achieve personal happiness in life. Existential crisis, not you. You're not going to have one of those because you made it through a really long physics video, and that means that you can make it through anything. This video is over.